Machine learning, ML, refers to the use of algorithms that identify patterns within data and use those patterns to make predictions, classifications, or decisions. Unlike traditional statistical methods that rely heavily on assumptions about data distributions, machine learning is designed to handle large datasets, high-dimensional variables, and complex nonlinear relationships. In investment management, ML is increasingly applied to security selection, risk management, fraud detection, portfolio construction, and economic forecasting. Key terminology includes target variables, which represent outcomes to be predicted, features, which are explanatory variables, training datasets used to fit models, and hyperparameters that determine how algorithms learn from data. Machine learning techniques are generally categorized into supervised learning, unsupervised learning, and deep learning. Supervised learning uses labeled training data in which the target variable is known, enabling the algorithm to learn relationships between inputs and outputs. Common applications include predicting stock returns, estimating default probabilities, and forecasting earnings surprises. Unsupervised learning differs because no target variable is provided. Instead, the algorithm seeks to discover patterns, structures, or relationships within the data itself. Deep learning utilizes neural networks with multiple layers to solve highly complex problems involving image recognition, natural language processing, and other nonlinear tasks. One of the most important challenges in machine learning is overfitting. Overfitting occurs when a model becomes excessively complex and captures random noise rather than meaningful patterns in the training data. Although an overfit model may perform exceptionally well on historical data, its predictive accuracy deteriorates when applied to new observations. This problem is particularly common when a large number of features are included relative to the available sample size. In contrast, underfitting occurs when a model is too simple to capture important relationships. Successful machine learning requires balancing model complexity to achieve strong performance on both training and future datasets. The trade-off between bias and variance is central to addressing overfitting problems. Bias error arises from overly simplistic models that fail to learn sufficient information from the training data, while variance error results from models that fit training data too closely and fail to generalize. As model complexity increases, bias typically decreases while variance increases. Analysts seek an optimal balance that minimizes total prediction error. Techniques such as regularization, cross-validation, feature selection, and model pruning help reduce overfitting. Fitting curves are often used to visualize how training error and validation error change as model complexity increases, helping analysts select an appropriate specification. Supervised learning algorithms are widely used in financial applications because target outcomes are often observable. Traditional multiple regression remains an important supervised learning technique for predicting continuous variables. Penalized regression models, such as ridge and lasso regression, improve prediction accuracy by reducing the influence of less informative features. Logistic regression is used when the target variable is binary, such as default versus non-default. Another popular supervised learning method is the support vector machine, SVM, which identifies optimal decision boundaries that separate categories. These algorithms help analysts forecast returns, classify securities, estimate risk, and support investment decision-making. Classification and regression trees, CART, represent another important supervised learning approach. CART models recursively divide data into smaller subsets based on features and decision rules that minimize prediction error. For classification tasks, the objective is to assign observations to categories, while regression trees predict continuous outcomes. The resulting tree structure provides an intuitive and visual representation of the decision process. To prevent overfitting, analysts may limit tree depth, restrict the number of nodes, or prune branches with minimal explanatory power. CART models are widely used for fraud detection, stock selection, credit analysis, and other financial classification problems. Ensemble learning improves predictive accuracy by combining multiple models rather than relying on a single algorithm. One approach aggregates heterogeneous learners, where different algorithms contribute votes toward a final prediction. Another approach aggregates homogeneous learners through techniques such as bootstrap aggregating or bagging. Random forest models are a particularly important ensemble method that combine numerous classification trees built from randomly selected observations and features. Because each tree is slightly different, errors tend to offset one another, reducing noise and improving predictive stability. Random forests are frequently applied to asset allocation, credit analysis, and forecasting complex financial outcomes. Unsupervised learning focuses on discovering hidden structures in data without predefined outcomes. Clustering algorithms group observations with similar characteristics, enabling analysts to identify natural segments within financial datasets. Applications include grouping securities by risk characteristics, identifying market regimes, and detecting unusual observations. Deep learning and reinforcement learning extend machine learning capabilities further by employing neural networks that learn complex nonlinear relationships and improve through feedback mechanisms. These advanced models excel in environments involving large datasets and intricate interactions. Collectively, supervised, unsupervised, and deep learning methods provide powerful tools for extracting insights, improving forecasts, and supporting modern investment management decisions.